students, welcome to Nuclear Physics Lectures. I'm Dr. Parvez Ahmad. In these lectures, we will talk about the four fundamental forces and their properties. So, what are the four fundamental forces that exist in nature? What are the particles which been responsible for carrying these forces? And what are the things and what are the objects in this universe and which these forces basically they are acting on? So let's talk our discussions on these forces. So you know that the first force that is well known and this universe that is called the force of the gravity. The force of the gravity is actually being carried by the particles that we call gravitons. So graviton is the particle that basically carried the force of the gravity. But be remember that graviton they are not yet being observed, are not yet being discovered. I mean, the scientists they're just trying for its observation. I mean, the scientists they are busy on observations of this kind of force, but still, I mean, they have not observed the gravitons. And this kind of force is basically is acting on all the forces, and this being explained by Newton's law of universal gravitation. I mean, the magnitude of this force is proportional to the product of masses and inversely proportional to the square of the distance between their centers. Uh, the second force that is known is called the weak force. The weak force is basically carried by the boson, that is the charge and the neutral boson, and this kind of the force is being acts on the quartz and the lepton. I mean, this force basically acts on the quartz and the leptons. The third force that we have is called electromagnetic force. The electromagnetic force is carried by the particles that we call the photons, the chargeless and the massless particles. I mean, the photons, the chargeless and massless particles. This been responsible for carrying the electromagnetic force, and this force basically acts on quarks and charged electrons and the charged bosons. The fourth force is called the strong force, which also known as the strong nuclear force, is carried by the particles gluons, and this kind of force acts on the quarks and gluons. So let again discuss in more details about the fundamental forces. So let's start the discussions with the strong force. So as we discussed on the on the previous slide, that the strong force, I mean, this is the force which is responsible for holding the nucleus together. You know that inside the nucleus we have the charged particles like the protons, and the charged particles are the neutral particles, the neutrons. So you know that I mean, basically we know that the charged particle, that is the protons, they might have repel each other's, and the question is that the charged particle they repel each other is how the nucleus is stable. So we remember that it's the strong nuclear force which has been responsible for holding the charge and the uncharged particles. Is the charge and nuclear, the charge and the neutral particles are holding together inside the nucleus. So the strong nuclear force is responsible. I mean, it's the force which hold the nucleus together. In other words, we can say that it is the force which hold the nucleus inside the nucleus together. The strength of this force is 1, and the range of this particular forces that is in the range of 10 raised to power minus 15. So what is mean? It's mean that this force can act in the range of diameters of a medium-sized nucleus. I mean, we have the distance between the nucleus in this particular range, that is in range of 10 raised to power minus 15. I mean, within this particular range, we say that the strong nuclear force will have this particular strength. And the particles gluon basically I mean, the particle which carry we carry this kind of force. I mean, the strong force has been carried by the particle gluon, which was called fermion, are the nucleons. I mean, the proton and the neutron, they basically carried this kind of force, the strong force. I mean, it's the strong force which keep the nucleons inside the nucleus together. The next force is the electromagnetic force. The electromagnetic force is basically felt by the charged particles inside and outside the nucleus. I mean, you know that the charged particle, the same charged particle can repel each other, and the unlike charged particle they can attract each other. If you compare this kind of force, the electromagnetic force, with that of the strong force, so the comparative strength is 1 by 1 by 137, that is 1 divided by 137. This is the comparative strength of the electromagnetic force. I mean, if you compare that the strength with the strong force, so the strength of the electromagnetic force will be equal to this much. The range of this kind of force is infinite. I mean, there is no finite range of this kind of force. I mean, it can uh, this kind of force can act at any distance depend upon. It can be better explained by the Coulomb law. You apply the Coulomb law, that is F is equal to K Q1 Q2 divided by R square. It's dependent upon the Coulomb law. You can better explain the force or the range of this kind of force. So here we can say that this force can act up to infinite distance. The particles which has been responsible for carrying the electromagnetic force is the photon. You know that photons they are massless particles, chargeless particles, but they have spins equal to 1. That's why we call them as a boson. Then we have the electroweak force. You know that the electroweak force is being carried by the boson, that is the charge and the neutral boson, and this being responsible for the neutrino interactions and is also induce beta decay. The comparative strength is 10 raised to power minus 6. The range of this kind of force is up to 10 raised to power minus 18 meters. So what it means that 0.1% of the diameters of a proton. And this kind of force is being paired by the intermediate vector boson, that is the charge and neutral bosons. The mass of these particles is greater than 80 giga electron volt, and again the span is equal to 1. The fourth force is called the force of the gravity, and the force of the gravity is being filled by between the two masses. I mean, whenever we have two masses, so all these masses they will have the force of attractions. So force of gravity is always attractive in nature. The strength of this force is, if we compare with the strength of the nuclear force, is equal to 6 into 10 raised to power minus 39. I mean, this is the comparative strength of the gravity, force of the gravity, and its range is again we can measure this force by applying the Newton law of universal gravitation. According to that law, the range of this force is infinite and it can be felt up to infinite distance, so that at a far distance it can be weaker, and for the smaller object it can be infinite smaller in dimension, smaller in the quantity, but still it can be felt there. So it's being felt or being carried by the particle that we call gravitons. Graviton yet to be discovered. The mass of graviton is 0, but the span of the graviton is equal to 2. These are the particle graviton, basically the particle which yet to be discovered. So the questions that normally the people have in mind, that what actually the fundamental forces do. So let's start the discussions, just like you can see it here in this particular figure, in this particular pictures. So what about the strong force? The people might ask the questions that what actually the strong force do. So the simple answer for this question is the strong force basically bind the nucleus of an atom. In other words, inside the nucleus it binds the protons and the neutrons, and inside the neutrons and proton it is bind the quarks. So what actually the final consideration, that it's bind the nucleus of an atom. So it's a sort of the binding force. What about the weak force? what actually the weak force what the weak force is responsible for. So the weak force basically allows the radiations. So this is the force that allows the radiations, and you know that whenever you have a radioactive atom, so that radioactive atom is almost unstable, and it's moved toward the stability by emitting the particles, and along with that, it's the radiation occurring from that particular nucleus with the emissions of the energy. So weak force is basically responsible for allowing the radiations. Then we have the electromagnetic forces. So what basically the electromagnetic force do? The electromagnetic force actually hold the electron and space around the nucleus. This is the key responsibility of the electromagnetic force inside the atoms. It's hold the electron and space around the nucleus. So what the gravity do? Just like the electromagnetic force, the force of gravity hold the galaxies together. It's according to Coulomb, according to Newton law of universal gravitation. That is, the greater the masses and the universe, the more the more powerful the force will be between those galaxies or those satellites or those heavenly object we have. So depending upon the masses, the heavier masses we have, the more powerful the force of gravity will be. So the force of the gravity is basically responsible for holding the galaxies together. So another important question that people always have in mind is that how we can unify these fundamental forces. So there have been different theories from centuries that how the people, how the scientists working in different fields of these forces, and how they done the effort to unify these forces. So let's start some of the discussion about the unifications of the fundamental forces. So let's start about the first effect that a scientist done in the start of the 19th century, where they're trying to combine the electricity, magnetism, and light. They combine these three. They combine the electricity, magnetism, and light in 1864, and they call them electromagnetism. This is the first attempt for the unifications of the fundamental forces. When the scientists, this was the era. You can say that something before the beginning of the modern physics, the scientists they were trying to unify the forces. So first they unify electricity, magnetism, and light into a single concept which they call electromagnetism. Then very recently they're trying to unify beta decay and neutrinos and to a single interactions which they call weak interactions. The first attempt was about the unification of electricity, magnetism, and light, and they are being unified into electromagnetism, and that happened in 1964. And then the second attempt was for the beta decay and neutrino. They are being unified into weak interactions, and when it happened in 1965. The third attempt was for the unification of protons, neutrons, and pions, etc. And they are being unified into strong interactions. When it happened in 1973. So in 1973, the proton, neutrons, and pions they are being unified into inside strong interactions. It was being found out that these kind of particles or these kind of particle inside the nucleus, they are being interacting with this particular force. So that's why they are being unified under this particular force, which is called strong interactions. And the last attempt was for the unification of the earth gravity and celestial mechanism, and that they unified universal gravity, and that happened far before than the other unifications. This unification happened in 1687. So these all earlier concepts have been unified into four basic mechanisms. So until 1973, we have these major unification, that is we have electromagnetisms, weak interactions, strong interactions, and universal gravity. Then what happened after 1973, or before 1973, the scientists introduced the concept of electro-weak interactions. So what happened what was the key idea in electro-weak interactions? So in the electro-weak interaction, the scientists basically unified the electromagnetism and weak interactions into a single interactions, and they call it electro-weak interactions, and that happened in 1971. Then space-time genome was being introduced for universal gravity, and that led us to the concept of general relativity. I mean, it's universal gravity. The concept was given by Newton's. So Newton concept of the gravity has been accompanied by the Einstein concept of space-time. So with that, we get into new era of universal gravity, and that was the time where the concept of general relativity has been introduced by Albert Einstein, and it is something, so we can say that the revolutions and the modern physics. I mean, that was the birth of the modern physics, general relativity, along with that special relativity. With that, we have the birth of the modern physics. So that's why Albert Einstein can rightly be called one of the father of the modern physics. So after that, we get in 1976 we get a standard model, and that standard models we trying to unify the electroweak and strong interactions. And I mean, what actually we mean to say that in 1976 a standard model has been developed, and that model the scientists and some of the key characteristics of the electroweak and strong interactions. On the basis of that, they unified into a single interactions in a particular model, and that particular model they call it standard model. So when it happened in 1976. There have been advantages and disadvantages of that model that we can discuss later on. I mean, some of the lectures in this particular course. So what happened after this, or what are we expecting after this? So the scientists, they're still trying. I mean, you know that the three of major interactions that they are being unified into a standard model. But now the scientists, they are doing their level best to combine the standard model with the general relativity. But you know that the work is still in progress. The people around the globe, they're working day and night, but till date, still we have, though we have some perceptions, we have some of the work, but that the work still not come out with a standard which being accepted universally, just like we have previously. That's all for these lectures. So see you in next lecture with further detail with some of the key concept and the particle physics. So till then, bye bye.